Okay. Today we're going to be doing mixtures and solutions. So a mixture is just a group of two or more chemical components that are not chemically linked together. So what that means is they're not bonded together, they're just mixed up with each other. And there are two main types of mixtures, which can be separated into three more specific types. Heterogeneous means that it's not completely even throughout, they're like bumps throughout. So like heterogeneous would be like a bag of Skittles, there are multiple colors. But homogeneous means that it's even throughout. It's the same everywhere, which would be like, I don't know, Skittles of all the same color. So for heterogeneous, you have suspensions. And in suspensions, they have relatively large particle sizes. They are not dissolved. And given time, the particles will settle out at the bottom. Some examples of suspension would be mud, chocolate milk, stuff like that. Colloids, they have medium-sized particles. They are also not dissolved, but they can scatter light. So if you shine a light through some colloids, they will scatter light and you'll see that. And solutions, they are actually being dissolved. So there's a solute, which is the thing being dissolved. This can be salt, sugar, really anything. And it's being dissolved in the solvent, which is what is doing the dissolving. So water is the universal solvent. And we're usually going to be doing liquids, but it can be like anything, like water, alcohol, fat. So vodka is a solution. It's just water and alcohol. And there are many different ways to measure concentration of different solutions. These are all of them. We're not going to use all of them, but basically molarity is moles of the solute over the liters of the solvent. And what over moles, but liters is just a unit of measure of volume. Mass concentration is grams of solute over liters of solvent. Mole fraction is moles over moles, solute over solvent. Molality, which is different from molarity, is the moles of solute over kilograms of solvent. Mass fraction is just the mass of each divided by each other. Mass percentage is that times 100. Parts per billion is that times parts per million is that times a million. So the parts per million is 1. That means for every 100 things inside, that thing's one of them. Parts per billion is like the same thing, but multiplied by a billion instead of a million. Electronegativity and dipole-dipole forces. So in compounds, we already talked about electronegativity. Some elements like to hog the electrons in a compound, which causes more electrons to surround the electronegative atom. This can cause a dipole, which is a partial positive or negative charge, where one side has a partial negative charge and the other side has a partial positive charge. When one side is more electronegative, it's polar, but it has to be asymmetrical. So if you see CO2 here, they have dipole forces, like the carbon is more electronegative than the oxygen is more electronegative than the carbon. But the oxygens are in opposite directions from each other, so it cancels out. But water, it has a dipole moment because it has that degree of like 107. So the electronegative is pointed towards whatever direction the oxygen is. And we haven't talked about VSEPR theory or molecular structure or shape yet. But basically, you just need to know if it's symmetrical, it's never going to have a dipole moment. So these are the 3 intermolecular forces that we're going to do. And you have to remember that opposites will attract. London dispersion forces. So when you have a molecule or an atom or anything, the electrons are always moving and they have velocity. So at a certain moment, just randomly, there may be more electrons on one side than the other side, which causes a temporary dipole moment. And this can help induce a different temporary dipole moment in a nearby molecule or atom. Dipole is two permanent dipoles. So the positive side and the negative side are going to be attracted towards each other, and that's the permanent dipole. Hydrogen, H bonds, hydrogen bonds, they are a type of dipole force. It's just hydrogen and a more electronegative element, and these are the strongest intermolecular forces that we're going to today. So, since London dispersion forces are based off of the random movement of electrons, the more electrons it has, the more potential there is for a London dispersion force. So, the bigger the molecule is, the more surface area, the more it's branched out, those are going to have more London dispersion forces. So, pentane is going to have a bigger intermolecular force than methane, since it's bigger and also has more surface area. And on the bottom left one, I'd like to see if you guys could identify which direction the dipole moment is facing. Okay, so the dipole moment here is towards the red molecule, that's the oxygen. It's whatever direction the oxygen is facing, since oxygen is by far one of the most electronegative elements. And I forgot to mention this, but in the periodic table, electronegativity increases as it go from left to right and from bottom to top. So the elements at the very right hand top corner are going to be very electronegative, like fluorine, oxygen. If you see fluorine and oxygen, unless they're bonded to themselves or like fluorine and oxygen, it's almost always going to be more electronegative than the other one. So there's going to be a force in that direction. So on this model, for here, the dipole moment would be facing the oxygen. This one is a symmetrical molecule, so since it's symmetrical, they balance out and there's no net dipole moment. Here, it would face the oxygens again, and the positive side would be the nitrogen. And here is the same thing. So these have a lot to do with solutions because like dissolves like. So when you have two things like polar, they're going to dissolve each other. So if something has a net dipole moment, that means it's polar because it has more negative on one side and more positive on the other side. So since it will attract like onto the different sides of it, it will like stick together. Like in a water drop, you'll see how like it's curved, or like you can fill up the water a little bit higher than the cup, and that's because of adhesion, where the water likes to stick to each other. And there's also cohesion where water can stick to other things. Like if you ever put water into a glass tube, you'll see that it's not like just straight, the water level, it'll be like curved. That's because the water is being attracted to the glass, since that type of glass would be a polar substance. But if you put water in like a non-polar substance like oil, then they're not going to mix. So because the oil is going to stick to the oil and the water is going to stick to the water. So oil and water would be immiscible. This is a solubility table with common ionic compounds. You're probably just gonna have to memorize these. We won't have to do these today, but it's really useful to know. And I didn't really explain ionic bonding as well as I should have last time. It's water. Water can be a solvent. Water is actually called a universal solvent, so it's almost always a solvent. Solute is the stuff that's being dissolved. Solute is like salt. Water is solvent. Oh, can water be a solute? I'm not sure about that because we're mostly just gonna be doing solid and liquid today, but maybe. Like maybe it could be like dissolved in a different liquid. Okay, so I didn't really explain ionic compounds as well as I should have last time, but basically ions are just things that have a charge, right? So if they have they have a charge because they really want that full octet so they gain or lose electrons. And if it loses electrons, then it becomes positively charged, and they call those cations. If it gains electrons, then it becomes negatively charged, and then we call those anions. And they don't have to just be single elements. Like it can be a polyatomic ion where they have multiple atoms in the ion. And then how you name them is you take the cation first, and then you add the ion, and then you add the anion, and at the end of the anion, you just add IDE. For some, like transition metals and stuff, you'll have to add a Roman numeral in between it, but I'll get back to that if we have more time. Precipitation reactions. So a precipitation reaction is where two dissolved things, they react in the water to make a precipitate, where they create a solid substance and it just falls out of the solution. That's why it's called a precipitate. So in chemical reactions, they will indicate the states in parentheses after the chemical formula. So S, solid, L, liquid, G, gas, AQ is aqueous, meaning that it's dissolved in water. And how to write precipitation reactions, you really need to practice these if you want to get good at them. But for the molecular, there are 3 different types of ways to write a precipitation reaction. For molecular, you switch the ions. So the anion gets the different cation, and the anion and the cation, they just switch. And then you will look it up in the table. If it's soluble, put AQ, which means that it's still the ions, it's still dissolved inside. But if it's insoluble, put S, meaning that's the solid, that's the precipitate. For ionic, you'd switch the ions again, but you need to like write them out. Like you would do Na plus Cl minus instead of writing NaCl for salt, because you would separate the ions. And if a new substance is soluble, write S, and write the ionic one. It's the same thing, but you cross out the ions on both sides. So the spectator ions. Okay, so that could be like pretty hard to understand if you don't see examples. On the first one, that is the molecular formula. So the ionic one would be, hang on. So the charges at the end are just to indicate the signs at the end are just to indicate the charge. And that's the ionic formula. If you want the not ionic, then you just cross out the ones that are on both sides. So the SO4, you cross that out because it's on both sides, and the same with the sodium. Factors of solubility: temperature, stirring, surface area, molecular size. So temperature is the average kinetic energy of that substance. So if it has more kinetic energy, the molecules are bouncing around more and it has a higher temperature. Whereas if it's bouncing around less, that's less kinetic energy and therefore less temperature. So the higher the temperature, the more it's going to bounce around, which means more opportunities for it to break off and dissolve. Stirring, the more you stir, it's kind of the same concept. The more opportunities for collisions there are, and the more collisions there are, the faster it's going to dissolve. Surface area, like if you take a big block of salt and try to dissolve it with water, it's a lot harder than taking like little crystals of salt and dissolving it in water, because when you have little crystals, those have more surface area compared to the volume. So it's really easy for just the water to surround it and dissolve it. But if it's in a bigger like shape, then it's harder for it to do that. And molecular size. So if there are two things that are like equal and all other different characteristics, the one that's smaller, the smaller molecule is going to dissolve faster. Emulsions. Okay, so there are two main liquids that we eat a lot, water and fat. But water is polar. It has that oxygen in the top. And fat is not, because it's mostly their forces mostly balance out. But because that they cannot mix. Because the water's gonna stick to itself and the fat's gonna stick to itself, and they're not gonna want to be together because they don't have the same force dipose. So emulsions can help bring those two together. So we call something miscible when two liquids can mix with each other, but they're immiscible if they cannot be mixed with each other. So water and oil, they're immiscible. But emulsions can help bring them together. So some emulsions work by adding starch to thicken the liquid. These are like speaking in the context of food. The thicker the liquid, the more resistance there is to things falling out. So if you put a lot of starch in the gravy, then it's a lot thicker, so it's a lot harder for like that fat to fall out of the emulsion. But some people don't consider those real emulsions since they're not like chemically bound. Some people say that if you want to be considered an emulsion, you have an emulsifier. And emulsifiers and stabilizers, they work to attach to both sides of them. So the water and the fat. So a large example is proteins. Proteins are really large molecules. I think you learned about this in biology, where some parts can be polar, which means they like water because water is polar, and some parts are nonpolar, which means they like fat, since fat is also nonpolar. So this can help attach the water to one side and the fat to one side, and then they're bound together. So these are a bunch of examples. The gravy, the starch, dairy, just in general, it has a lot of proteins in dairy, which attach to both sides and help bind them together so that the baby calves can get nutritious milk. Garlic aioli, surprisingly, garlic is an emulsifier, and how you know something is an emulsifier instead of just thickening it is that for emulsifiers, the more you add, the thicker it's going to get. If something is just getting it thicker, then the more you add, the less thick the liquid will get. Mayo, there's a lot of proteins in eggs that also can help bind both of them together, and hollandaise sauce, which I believe also uses eggs. This is a diagram of salt being dissolved in water, which can really help you visually recognize that the hydrogens have that partial positive charge, and so they're going to be attracted to the negative ion, which is salt, Na, sodium, and the oxygens have a partial negative charge, so they're going to be attractive to the positive one. I misspoke. The negatively charged one is the chloride, and the positive charged one is the sodium and NaCl, which is table salt. Okay, so when the water is boiled or frozen, it's like the structure of it is changed. So like temperature, like I said, is kinetic energy. It's the average kinetic energy of the substance. So the more kinetic energy it is, the faster they're going to bounce together and the more they're going to bounce. But the cooler it is, they're just going to like come into a crystalline structure. But when you add salt, like any solute really, it makes it harder to boil and freeze because when it's frozen, it's like disrupting the structure between the different water molecules, and when it's boiling, it's like harder because it's in between all the water's molecules. So when you add a solute, it causes the boiling point to increase, which means it gets harder to reach the boiling point, and it makes the freezing point decrease, which is why I put salt on the roads. Salt helps the water's freezing point decrease, and if the freezing point is decreased, that means it has to get even colder for it to turn into ice. But you might have heard that adding salt to water makes it boil faster. While it does cause the boiling point to increase, it also changes the specific heat, and we're going to talk about specific heat more tomorrow. So we can calculate the change in the boiling or freezing point by using K, the equation K times M times I, where K is the constant. So for every substance, there's going to be a constant. For like water, you can look it up, like what's the boiling point, what's the boiling point elevation constant of water, and you'll get the number. Times the molarity, and the molarity is the concentration of the sol or the solute in the water. So that molarity is moles over kilogram, and the reason that it's molarity and not molarity is that molality has the solvent in kilograms instead of liters, and when it's mass instead of volume, the mass can be changed in temperature, whereas the volume will increase with temperature. And I is just the Van 't Hoff factor, which sounds really fancy, but it's just how many things there are after it dissolves. Like for covalent bonds, like sugar is covalent, it's not going to break apart in the water. So that's just one. But for salt and most salts that we're going to be doing, it's the two because it splits into the anion and the cation. So like in the diagram where the salt was being dissolved, they're no longer like a salt crystal inside the water. It's all anion. It's all ions inside the water. So usually it'll be two for anything ionic. Taste / digestion. Certain flavors and nutrients can only be dissolved in certain liquids. So vitamin A is fat soluble, while vitamin C is water soluble. So if you want to like fully access the nutrients inside, you might need to add like multiple different things. And adding different things inside can also help bring out the flavors, like adding vodka to tomato sauce. There are probably a bunch of alcohol soluble flavor compounds in tomatoes, so which like aren't soluble in water. So if you add the vodka, even though you can't taste it, it will still bring out the flavors of the tomato sauce. Equilibrium constant. So this is like a more complex thing, but basically KSP is just like at equilibrium. So in chemical reactions and stuff, there's forward and there's backward. So equilibrium is just when the forwardness of the reaction is equal to the reverse reaction. So in this case, solubility, the equilibrium constant would just be what it is when it's dissolved as much as it can. And how you calculate it is the concentration of the cation raised to the coefficient. So remember in the chemical reactions, we were balancing those and you have to add the coefficients before them in order for there to be a balanced number of each element. That is what it's being raised to. And it's the anion and that, and what the relative concentration of the anion is. So at a certain point, you can measure the concentrations of the cations and anions. And if that's more than the equilibrium constant, that means it's been super saturated. If it's less than it, that means it has not been saturated yet. And if it's 1, that means if it's the same as the constant, that means that it's at capacity. So how supersaturation works is when you heat liquids to higher temperatures, they can hold more of the solute. So if you boil water and then or heat it up and then add salt to it, then it can hold more salt than room temperature water would. And KSP is really helpful in like different problems where you have to calculate certain things, like calculate the molarity or the different concentrations of things from it. But we're just gonna do those if we have more time. Okay. Which of the following intermolecular forces is the strongest? Yes, this one is C. Oh. Sorry if I went too fast for you guys. But hydrogen bonds are stronger than London dispersion forces and dipole-dipole forces because London dispersion forces are only temporary and caused by random changes, so they're pretty weak. And hydrogen bonds are a subtype of dipole-dipole, but they have a much higher electronegativity difference. Okay, this one is probably a little bit confusing since I didn't go over this exact example, but mud is a suspension because it has very large particles. Like the mud, the particles are like the different dirts in the little pieces of rock inside. So that is a very large molecule compared to what other types of molecules are there. which is colored in suspensions, and it's definitely not being dissolved inside the water. Like the dirt isn't being dissolved in the water, so it's not a solution. And if you actually take mud and like you let it wait for a little bit, you know how like the dirt would settle to the bottom? That shows you that it's a suspension, because suspensions were like, if you wait a little bit, the particles will go down to the bottom. Okay, yeah, this one is false, because the same like dissolves like, which is really important. So oil can not dissolve water because they don't have the same, like non-polar dissolves non-polar, polar dissolves polar. Okay. This one is true. So milk is an emulsion where water and fat, they're usually immiscible. But in this case, they are immiscible because the emulsifier, which is the protein, connects the water and the fat together, so they don't have to separate now. They can be friends in a way. So this one's true. Okay, this one is false. Adding salt would make the freezing point lower because it would be even harder to freeze the salt water, which is why the oceans don't usually freeze in the winter unless it's very, very cold. Okay. So we have some extra time. So actually a lot of extra time. So I'm going to answer your questions first, and then we're going to do something else. So feel free to like ask any questions or ask me to go back and explain another slide. Is the collision like dissolved oxygen and flow in water? I don't really understand what you trying to ask with that question, so could you like specify more? Oh, could I send the link? Yeah, they will be found in the Kid Teach Kid website, but I'll just send the link in the chat. Okay. I'm gonna see if there are more questions, but we still have like 25 minutes, so we're gonna do more stuff after. Okay, so we are going to do more stuff now. Didn't understand the dipole-dipole concept. Okay, yes, I can. Hang on, let me share my screen first. Okay. So electronegativity is when different elements, like some elements like to hog the electrons more when they're in that compound. So, and it's very important to understand the periodic trend for it. The periodic trend is as you go to the right and to the top of the periodic table, the more electronegative that element is. So oxygen and fluorine, those are extremely electronegative. That's because as you go to the right, they get closer to that full octet. So they want those electrons more. And the molecule, when there is a more electronegative element and a less electronegative element, then that more electronegative element is going to hog the electrons more, and the electrons will spend more time around that element. So like in water, the oxygen has the electrons around it more often than the hydrogen. So that is a permanent dipole where the oxygen is more negative and the hydrogen is more positive. So the dipole-dipole force is when there are two permanent dipoles like that, and the positive side is attracted to the negative side because opposites attract, and that's how they like hold together. Does that answer your question? Okay. So we have a lot of time left, so we're gonna do some problems. These are actually from high school psychology for Chem Lab. Okay, we'll do 3 first because that does not involve drawing a Lewis diagram. True or false? H2O is a polar molecule. This one is pretty important. Hang on, let me share the correct screen. Okay, so number 3, is H2O a polar molecule? Yes, okay. Yeah, water is definitely a polar molecule because the oxygen is incredibly electronegative, and that's actually a hydrogen bond there. So the oxygen has a lot more of that push don't give charge. And it's not symmetrical because it's like it's like a bent shape where there's an angle in between them. Okay, why is methanol miscible but methane not? These are pretty hard questions, so it's okay. Okay, yeah. So the methanol, it has that OH at the end, and that O is really electronegative, so there's a partial charge there, which makes it polar and like dissolves light. But methane, one, it's more of like a tetrahedral shape, so, and the carbon is not as electronegative, so the difference is not, and it's not as polar. Okay. This one would be pretty hard without like memorizing it since I went over them really briefly. So I'm just gonna tell you these. Okay. Moles of solute over liters of solution, that is molarity. Molarity is actually really commonly used. Okay, moles solute over kilogram solvent, that's molality. And molality is used a lot for like coagulative properties since the it's just the mass and not the volume. And moles over moles, that is the mole fraction, I believe. Yeah, that's mole fraction. Okay, mass over mass is the mass fraction. Number 2 is parts per million, since it's the mass fraction times a million. So that means for 1 part, there's going to be, it's a 1 of that thing out of a million. Number 3 is parts per billion, as it's multiplied by a billion. So if it's 1 part per billion, that means there's 1 of that thing out of a billion particles. Okay, this one is fun. 20 grams of sodium chloride is dissolved in 2.5 kilograms of water. And you need the periodic table for this, and this also uses the moles and periodic table that we learned yesterday. So you guys can like do this, and then I'll write my solution in the chat. The molality, it will be a number, so it's not just an AC. No, because molality is moles of the solvent over the kilograms. So the kilograms is 2.5, and you need to figure out how many moles there are. And we learned this last time where the molar mass is moles over grams. So we want the number of moles at the end. So we're just going to multiply. So we're going to do grams, 20 grams divided by the molar mass, which will be grams per mole. So the mole is left up at the top and the grams cancel out. Okay, I'm gonna write this. Okay. Oh, and to determine the molarity, you need to find the amount of liters. And to find the liters, you need to use ideal gas law because we only know the amount of moles there are, and I'm assuming that it's at standard temperature and pressure. And from that, we could use the ideal gas law to figure out how much water there is in volume. But we're not going to do that. Okay, this is one. So we already know the molality of it. So from the molality, we can calculate the boiling and the freezing point. So you guys should attempt it, and I'm gonna write my solution. Okay, so hopefully you understood that. It's just the constant which they give you times the molality, which we calculated in the last question, times the Van Hoff factor, which is 2 because it's an ionic compound. Oh, okay, yeah. Oh, on that question. Yeah. Okay. Oops. Okay. Number 9. Okay. So I did the conversion for you from 75 grams to liters. So you just need to figure out how many moles of salt there are. Okay, so we just had to calculate so this one will be B because we had to calculate the molarity. Molarity is the moles over liters. And we had to figure out the number of moles of salt, which would be 32 divided by the molar mass. And the molar mass is the molar mass of sodium plus chloride. And we converted the 75 grams into liters, which gave us the volume of it. So then we just divided the moles of salt over the liters of water. Okay. This is cool. Saturated, unsaturated, and or supersaturated. Okay, so saturated means that it can't take any more salt. Unsaturated means that it's not fully like it can still get more dissolved inside. The water can still take more salt. And supersaturated means that they heated up the water, and heated up water can hold more salt. So they heat it up and then they added more salt. So now it's oversaturated. It has more salt than it's supposed to have. So if the salt dissolves after mixing, that means that there was still room for it to dissolve, which means that it's unsaturated. If none of it dissolves and nothing else happens, then that's just saturated. It's just full. And if a crystal starts to form in solution upon addition, that's supersaturated because there's so much salt inside. Once you add the additional salt, that it can start crystallizing around it because you just added a part where it can crystallize and join that. Okay, these are about redox. Okay, pure water always boils at 100 degrees Celsius. True or false? Okay. This one is actually false because the boiling point is not only affected by temperature, it is also affected by the pressure. So at sea level, it's always 100 degrees, but as you go higher, it will start to boil at lower temperatures. Okay, silver chloride is soluble in water. So for this one, you look at the solubility table that is in the slides. Silver is Ag, by the way, and chloride is Cl. Okay, so for this one, you just look at the solubility table that is in the slides. You go to Ag and Cl, and you can see the table says that it's insoluble. So it is not soluble. Other than that, you'd have to memorize it. Oh, okay. Okay, so we have 3 minutes left, so I'm gonna end it now. And I hope you guys had fun. Do you guys do like Sayoli or anything at your school? Like, why did you decide to come here today? Okay, your next class is forensics. Forensics is a lot of fun.